Electrolysis. So now we're going to switch gears from galvanic cells to talk about electrolytic cells. So we talked about all right before this that galvanic cells happen from spontaneous reactions, so there's no extra input of power that needs to be done in order for that redox reaction to occur. Now, electrolytic cells are completely the opposite, so this is non-spontaneous reaction. In an electrolytic cell, the electrical energy is used to produce a chemical change and make a non-spontaneous reaction happen. So a spontaneous reaction, again, a little review, is when you have like a car rolling downhill. There's no work or effort you have to put in to make that car go downhill. Non-spontaneous is kind of the opposite of that. If you were trying to go uphill, you would have to constantly push or add work in to make that happen. Otherwise, it would just roll down and it wouldn't occur. So what happens in electrolysis is that an electrolytic cell makes the energy to have a non-spontaneous reaction actually happen. And the process of electrolysis specifically involves forcing a current through a cell to produce a chemical change for which the cell potential will then be negative. So for our galvanic cells, we're looking for a very spontaneous reaction, a positive cell potential, the tendency to occur. Now we're kind of looking at more negative values. So here's a great little picture diagram of a galvanic cell and an electrolytic cell. So what do you notice between these two examples? You have an anode and a cathode, but they switched places. And notice how for an electrolytic cell, you have a power source that is putting in power. Where in a galvanic cell, this is collecting power. So it's a little bit different because the electrons aren't just traveling because they want to. These electrons travel because of that input of the power source. So electricity is used to make a non-spontaneous reaction happen. Your anode is positive and your cathode is negative. And it can be done in one container or a separate container. So you can notice here that the electrons are moving from the anode to the cathode, so that hasn't changed. But the cathode is on the left and the anode is on the right. Now, there's two types of electrolysis that we look at, the one in water and then the one in aqueous solutions. But first, let's talk about the electrolysis of molten salts. So electrolysis of molten salts that would be if we had sodium chloride, for example, a molten salt, which would be sodium and then chlorine. But these are not aqueous, so that's what's different here. The two half reactions would be sodium to sodium solid, chlorine ion. Here you notice that this is the cathode reaction, it's the reduction. This is the anode, this is the oxidation. So the sodium metal forms at cathode and chlorine gas forms at anode. Now, why do you think this would be an example of electrolysis? We know that sodium chloride is very common and we use it all the time. Why would this be electrolysis? Notice how sodium is being reduced. We know that metals tend to lose their electrons, so this is not spontaneous, right? A metal is not just going to gain an electron, and chlorine, which is a halogen, a very reactive nonmetal, is not going to easily lose its electron. So the formation of non-aqueous, so molten salt, is very not spontaneous, so it needs that extra room or extra energy to actually make this reaction happen. The sodium metal forms at the cathode and the chlorine gas forms at the anode. This is how sodium solid is actually produced. It's not found regularly in nature. So I should say sodium solid, not sodium chloride. Perfect. So we can't really just find sodium solid regularly, so that's made through this non-spontaneous reactions. Now, aqueous electrolysis is the electrolysis of water, when water is present and can also react. To decide what will happen, we consider all possible reductions and oxidations. You choose the easiest one of each. So again, we're switching gears to electrolysis. We're thinking of cells, still cathode and anode, half reactions. What we're doing here is most of these reactions are not normal looking in a way. They are non-spontaneous. So the electrolysis has that extra energy to actually make this reaction happen. Now, when you don't just have a metal and a non-metal, but you actually have water in it, the electrolysis can still occur, but you have to kind of think of what is everything that's present, what can also react, and then which one would be the easiest to actually do, because that's still going to be more potent and will happen more than things that are harder to actually go forward in a reaction. So here you can see, for example, the electrolysis of water. You have the anode reaction and the cathode reaction. And you have your net reaction. Now again, hydrogen ions and hydroxides will also always sum to water. And you know that the reverse reaction of water, if we were to flip this one here on the bottom, would be a way to force a reaction by electrolysis, right? Because we know that you can't just decompose water like this. We would need electricity to actually split up the hydrogen and the oxygen from water. Electrolysis in a mixture of ions. So suppose that you have a solution in an electrolytic cell that contains copper, silver, and zinc. If the voltage is initially very low and it's gradually turned up, in which order will the metals be placed out onto the cathode? So you would look at all your possibilities, right? You have silver, copper, and zinc. And let's say that at first your voltage is really low. And then what happens is gradually increases because the metals are going into the cathode. What happens is that the more positive cell potential energy means the more the reaction has a tendency to go to the right? It has a more of a tendency to occur in the reduction process. So you choose which one is the most positive, because again, that's the most spontaneous, most likely to occur in reduction, which would be silver. So then silver is your most likely, then it would be copper, and then it would be zinc, because zinc is your smallest. Now, when we're talking about these type of electrolysis, there's always some complications. It depends on the speed of the reaction, the amount of energy needed to actually activate the reaction, different concentrations, but most of the time we can look at the cell potential and the different components of a reaction to see and predict a good idea of what direction the electrons will go and whether this reaction will occur or not. So you're always looking at your possible reductions and oxidations, and you look at the values that are easier, right? So you're looking at which one is easier to happen, which is going to be your more positive value. So for the electrolysis of mixture of ions or the one in water, you would look at which one has a higher electrode potential, and that one will happen easier. So you look at all of your oxidation reactions, all of your reduction reactions, and choose the easier one. Now we can put this in with stoichiometry and solve for electrolysis to kind of put together what type of problems that you could see. So when we consider the stoichiometry of an electrolytic process, which refers to determining how much chemical change occurs with the flow of a given current for a specified time, the steps to solve a stoichiometry problem would be: you have current and time, quantity of charge in coulombs, moles of electrons, moles of copper, grams of copper, if copper was specific here. Let's put that into a practice problem. How long must a current of 5 amps be amplified to a solution of silver ion to produce 10.5 grams of silver metal. Alrighty, so we have this 10.5 grams of silver metal and these 5 amps. I know that 1 amp is equal to a coulomb over second, so I could say that 5 amps is equal to 5 coulombs per second. Well, what else do I know? I know that silver was reduced, so silver ion gained an electron to become silver metal. And this is a 1-to-1 ratio. And I want how long, right? So I'm trying to get the seconds. So I need to get rid of coulombs. But I also have this 10.5 grams. Well, I know that I can use molar mass to get moles, and then Faraday's constant to get coulombs. Remember, Faraday's constant is 96485 coulombs per mole of electron. So I can use Faraday's constant to use my coulombs and get seconds. So I need moles of electrons. Well, I can get moles of electron from my 1-to-1 molar ratio, so I start with molar mass. So I have 10.5 grams of silver times 1 mole of silver over 107.868 grams of silver times, now I have grams of silver and I need mole. Well, I know that 1 mole of electron, right, over 1 mole of silver, that's from my balanced reaction up here. Then I can use my Faraday's constant to get coulombs. And now I can use my seconds over coulombs to get my time. And I used minutes because usually seconds would be way too many. So then there's 60 seconds in 1 minute. You can see grams cancel, moles of silver cancel, mole of electron, coulombs, seconds. You plug everything in, you get 31.3 minutes. So this is really similar to all the different stoichiometry problems that you've already done. You know that you have different conversions. So whether you have a reduction or an oxidation, you want to write that out so that you can kind of see a structure. Faraday's constant always gives you coulombs over mole electrons. So you could use that to get coulombs, you could use that to get rid of coulombs or mole of electrons. If you have mass, molar mass is always a safe bet to kind of throw in there. And then just remember amps is equal to coulombs over time. So whether you need to use your time or you need to get rid of that unit. So it's kind of just puzzling it together in all the different types of stoichiometry problems that you've already done in the past to help you figure things out for how long a current would take for this electrolytic cell. So this is for electrolysis because we're putting current into this reduction process. Now think about it. Does silver really want to be reduced? No, it's not very common at all because we usually want a oxidation because silver loses electrons. It's not going to gain electrons. So this is an example of an electrolysis process. So if there was an extra question here saying, is this a representation of a galvanic cell or an electrolytic cell or electrolysis, you could say electrolysis explaining that, knowing that we had to apply current, which is kind of already a proof that this was a non-spontaneous reaction. Also, in the fact that we know metals want to lose electrons, they want to be reducing agents. They don't want to be oxidizing agents. They don't want to continually gain electrons. They don't like to be reduced. So great examples of what you'll see in your homework. Knowing kind of, all right, so an electrolysis process, an electrolytic cell still has an anode and a cathode, just like we talked about over here. Oops, right? The anode electrons are going towards the cathode. However, there's this power source that's going inside because it helps a non-spontaneous reaction to occur. And in the electrolysis of water, you have the anode and the cathode reactions that are occurring, right? And then in the mixture of ions, whichever ion has the more positive is the one that was more likely to occur. So when you have water and ions, you think of all of the possibilities. So you would write down every single half reaction possible for oxidation and every single half reaction possible for reduction. So I'm going to write an example here for the electrolysis of sodium chloride. So, for example, let's say that we have NaCl. So we know that my main components are, because NaCl is aqueous, sodium ion, chlorine ion, and water. Okay, then my next step would be, I'm going to think of all of my possible oxidation and all of my possible reductions. So I have sodium ion to make my sodium metal. This has negative 2.71. And then I have my water, because water can act as both. So these were my reductions, possible reductions. Now let's think of possible oxidations. For possible oxidations, we would have chlorine ion to chlorine gas and 2 electrons, and then our water. Now let's take a look at one at a time. So between the reductions, which one would be more likely to occur? Well, do you notice how water is a little bit more positive? So this one is easier. So this is the main reduction. Let's look at the oxidation. Well, water this time is a little bit. These are pretty closer in values. Negative 1.35 and negative 1.23 is not nearly as much of a difference as negative 2.71 and negative 0.83. So that's definitely something to notice as well. But if we're really looking at which one is a little bit faster, it would be water because it's more positive. So this would be the oxidation. However, in actuality, when the values are super close, it'll then depend on the concentrations. So if the concentration of chlorine is high, chlorine will get oxidized. It doesn't matter that the potential of water is just slightly more positive. If the concentration of chlorine is low, then water will get oxidized. So if the concentration is low, then you do look at the cell potential. But if it's high, then chlorine would just get oxidized. It doesn't matter that water is slightly larger. But you can only do this comparison when the values are fairly close. We can't do this with the sodium and the water reduction because of the fact that the values are very different. So all of this example was just to show you, again, I know it looks weird because you're thinking sodium does not get reduced, it gets oxidized, but these are non-spontaneous processes. So when there's a process, you're looking at all of your possible main components, writing down your half reactions, and then looking at which one is the most likely to occur, just slightly more positive. If they're similar, then you will look at the concentrations. And then again, you can use all of these different components in different questions. Like stoichiometry, the one that we did as an example over here.